In this classwork, we begin with problems where we already have like terms and we just need to combine them. So in 1a, we have 6 roots of 2 and 4 roots of 2. When I combine them, I get a total of 10 roots of 2. In part B, I have 2 like terms, the 5 roots of 5 and the understood 1 roots of 5. 5 plus 1 gives me a total of 6 root 5. Then I've got this 5 that has no root with it and is an unlike term and cannot be combined. So my final answer should be written as 5 plus 6 roots of 5. When I look at problems like 2a, b, and c, these are ones where I'm going to have to use the skills from section 8.3 in order to simplify the roots, and then once they're simplified, hopefully I can find ones that are like terms and can combine. So when I look at the root of 24, I go to my list of perfect squares. I see 25 is too big, so I try 16. 24 divided by 16 doesn't give me a whole number. I try 9, doesn't give me a whole number. 24 divided by 4 does give me a whole number, specifically 6. So I know to break this up into the perfect square root of 4 times root of 6. It's always a good idea to take the non-perfect square part, the part that's left over in a problem like this, and try dividing the next term by that to see if it gives you a perfect square. If I divide 54 by 6, I get 9, which is a perfect square. I should break this second one down into the root of 9 times the root of 6. If I now take out the perfect squares, so the root of 4 is really 2 root 6, and the root of 9 is really 3 root 6, I now can see that it's 2 plus 3 gives me a total of 5 root 6. When I look at 50, I would begin here with 49 as the first one less than it. 50 divided by 49 doesn't give me a whole number. 50 divided by 36 doesn't give me a whole number. 50 divided by 25 does, it gives me 2. So I can break this down into the root of 25 times the root of 2. If I divide 32 by 2, I get 16, which is also a perfect square. So I can break this down into the root of 16 times the root of 2. The root of 25 is 5, so I have 5 root 2. The root of 16 is 4, so I'm subtracting 4 root 2. 5 minus 4 gives me a total of 1 roots of 2. I can just write that as the root of 2. When I go to do part C, 40, the first one smaller is 36, so I do 40 divided by 36, I don't get a whole number. 40 divided by 25, I don't get a whole number. 40 divided by 16, I don't get a whole number. 40 divided by 9, I don't get a whole number. 40 divided by 4, I do. I get 10. So I can break this up into the root of 4 times the root of 10. If I divide 90 by 10, I get a perfect square 9. So I can break this up into the root of 9 times the root of 10. If I divide 490 by 10, I get 49, which again is a perfect square. So I can break this up into the root of 49 times the root of 10. Root of 4 is 2 root 10 plus 3 root 10 plus 7 root 10. 2 plus 3 is 5 plus 7 is 12 total roots of 10. So my final answer is 12 root 10 here. Continuing on, D asks us to take root 108 minus root 28 plus root 300 minus root 7. When I go to look for how to break down root 108, I'm going to start with 100. 108 divided by 100 doesn't give me a whole number. Divided by 81 doesn't. Divided by 64 doesn't. Divided by 49 doesn't. Divided by 36 does. Specifically, I can break this into the root 36 times the root of 3. My trick so far has been to put in what was left over to the next one. But when I divide 28 by 3, I don't get a whole number. So this means this second part is going to have a different like term to combine. So when we do the same process with 28, 25 doesn't go in evenly, 16 doesn't go in evenly, 9 doesn't go in evenly, but 4 does go in evenly. So I can break this up into the root of 4, and 28 divided by 4 gives me 7. With this term, I'm not sure what's going to be left behind, whether it's the 3 or the 7 or something entirely different. So I'm just going to try them in order. When I divide 300 by 3, I get 100, which is on my list of perfect squares. So I should break this up into root 100 times root 3. If I tried root 7, 7 wouldn't go into 300 evenly. Now when I see this root of 7, there's no perfect square that can go into it. I need to leave it as a root of 7, but the good news is I see something that's going to be root of 7 that we'll be able to combine with it. I could have tried putting in 4, seen it didn't work, and realized that there was no way to break that down further. If I now take the perfect squares out of the square root, 36 becomes 6, roots of 3, minus 4 becomes 2, roots of 7, plus 100 becomes 10, roots of 3, minus an understood 1, root of 7. 6 roots of 3 plus 10 roots of 3 give me a total of 16 roots of 3. Negative 2 roots of 7 minus 1 more root of 7 give me a total of negative 3 roots of 7. So my final answer would be 16 root 3 minus 3 root 7. In part E, I'm going to start with 294 by dividing by 100. Doesn't go in evenly. 81 doesn't go in evenly. 64 doesn't go in evenly. 49 does. 49 times 6 gives me 294. So when I divide 294 by 49, I get a remainder of 6. When I try and put that same 6 into 384, I do get a perfect square. Specifically, I get 64. So this becomes root 64 times root 6. When I try and put the 6 into 99, it doesn't work. So I realize there's a different like term that I'm dealing with here with the 99. I try 81, it doesn't go in evenly. 64 doesn't go in evenly. 49 doesn't go in evenly. 36 doesn't go in evenly. 25 doesn't go in evenly. 16 doesn't go in evenly. 9 does. Specifically, I can break this down to the root of 9 times the root of 11. The one that's going to be left behind that's not a perfect square is 11, so I try that into the next one. It does go evenly into 44. It goes 4 times, which is a perfect square. If I now take out the perfect squares, root 49 is 7, root 6. Root 64 is 8, root 6. Root 9 is 3, roots of 11. And root 4 is another 2, roots of 11. 7 plus 8 gives me a total of 15, root 6. Negative 3 and negative 2 combine to give me negative 5, root 11. So my final answer would be 15 root 6 minus 5 root 11. When I go to simplify the expressions in part 3, I see that the index number has changed to cube roots, so I need to be using my top list of perfect cubes. When I go to see what will go into 40 evenly, I start with 27, it doesn't work. Then I see that 8 does work. Specifically, 8 times 5 gives me 40. Since 5 is what's left behind, I'm going to try putting 5 into the second radicand. When I do 135 divided by 5, it gives me 27, which is on my list. So I now see that I've broken this down into 2 perfect cubes times the cube root of 5. When this comes out of the cube root, 8 becomes 2, the cube root of 5. The cube root of 27 is 3, so this becomes 3, the cube root of 5. 2 plus 3 gives me a total of 5, the cube root of 5. My final answer is 5 cube root of 5. When I go to do part B, I start on my cubes list with the largest one I have, 1,000. 4,000 divided by 1,000 gives me 4, so it does go in evenly. I can split this up into the cube root of 1,000, which I do know the cube root of, it's 10, times the cube root of 4. A lot of times when people see perfect squares under cube roots, they want them to come out, but in this case, 4 under a cube root does nothing for me. I know that the square root of 4 is 2, the cube root of 4 is a decimal. When I then say, well, what's left behind here is a cube root of 4, let me try putting a 4 into this 500, I would see that it breaks down into 125, which I do know the cube root of, times that leftover cube root of 4. The cube root of 1,000 is 10, so I have 10 cube roots of 4, plus the cube root of 125 is 5, so I have 5 cube roots of 4. When I combine them, 10 plus 5 gives me a total of 15 cube roots of 4.